In this video, I'm going to solve every question from the UKMT Junior Maths Challenge from 2017. That's one of the main maths challenges in the UK, usually taken by students aged 11 to 13, but often taken by younger students as well. And if you're preparing for that challenge, then take a look at my free course, Get Ready for the Junior Maths Challenge. In that course, you can practice all of these questions, as well as questions from other papers, and each question has a video hint and a full video solution. So you can have a go at the question, then watch the hint if you're stuck. That gives you really the best chance of getting the answer by yourself. Then you can see if it's right, and then watch the video solution if you want to. It's a really great way to prepare for the Junior Maths Challenge. Over at the course's website, I've got loads more courses to prepare for maths challenges and for school maths as well, so I really hope you will take a look over there. But if you'd like to watch the solutions here on YouTube instead, I'll get on with them now. I'll put timestamps below so you can jump to the questions you need, or if you'd like to work through the whole paper with me here, then we'll start at question 1 and you can pause the video at the start of each solution. So nothing to do apart from to work them out quickly. 2 minus 1 is 1, 2 divided by 1 is 2, 2 times 1 is 2, 1 times 2 is 2, and 2 plus 1 is 3, so the largest of these is 3, and the answer is E. So Nadia puts a cake in the oven at 11:40, and it's going to bake for an hour and 35 minutes. I want to see what time we're going to take it out. So I guess the way I would think about this is to chunk up the 1 hour 35 as 1 hour plus 20 minutes plus 15 minutes. And then 11:40 plus 1 hour takes us to 12:40. Another 20 minutes takes us to 1300. And then another 15 minutes takes us to 13:15 here. So we're going to take it out at 1:15, and that's the answer. As long as you remember there are 60 minutes in an hour, shouldn't have too much trouble with that one. We've got alternate angles here, sometimes called Z angles because of the sort of Z shape that they make here. So you need to know here that these alternate angles are equal, and also that the angles in a circle would add up to 360 degrees. So the x here is just going to be 360 minus 303, which is 57. And then this x is also going to be the same, so that's also 57, and the answer is D. So if you're good at fractions, you might be able to just write down the answer here, but if a download is 95% complete, what fraction is yet to be downloaded? So we're looking 100% minus 95% is 5%, so if I want to write a percentage as a fraction, I just put the number over 100, so that's 5 divided by 100, and then we simplify it down. So there's a common factor of 5 top and bottom here. 100 divided by 5 is 20, so this is 1 over 20, and the answer is E, 1/20. So you could actually work out 201 times 7 and 7 times 102 here, and that would be fine. You can probably do that reasonably quickly and subtract them. But if you really want to make the most of your time in the maths challenges, try to simplify the calculation. So, if I've got 201 times 7, and I'm going to subtract 102 times 7, so this is like I've got 201 lots of 7 and I'm going to take away 102 lots of 7. We'd really like to use the fact that this is the same as 201 minus 102 times 7. 201 minus 102 is 99, so I just want to do 99 lots of 7, right? And well, 99 lots of 7, that's just 100 lots of 7 minus 1 lot of 7, or 7. So you see I can get really quickly here that the answer is 700 minus 7, which is 693. So these sort of calculation tricks just give us a bit more time to do the later questions if we're going for those gold certificates. So I'm going to do this in a really efficient sort of maths challenge kind of way here. I'm not going to deduce the answer directly at all. So in the magic square, we know the diagonals, the rows, and the columns have to add up to the same total. Well, look at the answers. All of the answers have the same total for the diagonal. They're all 9 plus 6 plus 3. So we know right away here that the magic total here has to be 18. So I can just look along here. 5 plus 10 for this row is 15, so that one must be 3 to make it 18. 8 plus 4 is 12, that one must be 6. 7 plus 2 is 9, that one must be 9. And now I've got a completed magic square. Not saying that's the way to complete the magic square if we didn't have the answers, but we have got the answers, so why not? The aim of the challenge is to do maths directly, but it's to use all of these things as well, give yourself as much time as possible to do those later questions. Anyway, that's a great method, I think. The answer here is D, and the numbers are 3, 6, and 9, in that order. Okay, so we want to work out which of these will be in the middle when we put them in increasing order. And so I think we should just evaluate all of these expressions. So 2/3 plus 4/5, we need to put them over a common denominator of 15. So that would be 10 fifteenths plus 12 fifteenths here, so that will give me 22 over 15. This one will be just multiply tops and bottoms to get 8 fifteenths. This one I can put them over 4 and get 6 over 4 plus 5 over 4, which is 11 over 4. Dividing by a fraction, we turn the fraction upside down and multiply, so this is 2/3 times 5/4. So a 2 cancels top and bottom here, and I get 5/6. And multiplying tops and bottoms here, I get 15 over 8. So I'll just clear out my working so we can see these fractions clearly. Now, one possibility here is that we now try to put all of these numbers over a common denominator. It'd have to be, I guess, 8 times 15, or 120, and then we could just compare them directly. That wouldn't take too long, so we could do that. We could also just do this, in a more maths challenging way, and say, well, look, if the numerator is smaller than the numerator is smaller than the denominator, then it's less than 1. So the two smallest numbers here are clearly 5/6 and 8/15. They're both smaller than 1. All of the others have bigger numerators than denominators, so they're bigger than 1. So actually I want to work out which of these three numbers that I've got left are the smallest. Well, 11.4 is actually bigger than 2 as well, and 15 over 8 is quite close to 2. 16 over 8 would be 2. Whereas 22 over 15 is nowhere near as close to 2, right? It would have to be 30 over 15 for it to be 2. So it must be that A is the smallest of these three, and then the final answer is A. If you're not happy with that sort of logic, fine, just put them all over 120 and put them in order, but we're looking for the fastest ways to do this to give ourselves as much time as possible for later questions as well. Okay, so to work out the area of the triangle here, right, I can just do a half base times height, where I'm thinking of this as the base and this is the height, right? So half base times height here gives me a half times 2 times 4, which is just 4 centimeters squared. Now you can see that the triangle here is exactly half the area of the big rectangle. You could see that either by drawing a line down here and saying, well, that this area must be the same as this one, and also this one must be the same as this one, and then we can see that the answer to the question is just 4 times 2 then, which is 8 centimeters squared, which is B. You could also see that this triangle was half the area of the rectangle because you could measure it in a different half base times height, right? You could say that this is the base and this is the height of the triangle, the perpendicular height, and then the triangle would be a half base times height, and the rectangle would be just base times height. Either way, the area of the rectangle is double the area of the triangle, and so the answer is B, 8 centimeters squared. So it's quite a convoluted question here about as you like it, and we didn't have to really worry about that. In fact, you could almost cross the context out here, and it wouldn't make any difference to the answer to this question. It just says, which of the following is equal to the number of seconds in 1/1000th of a minute? Right, well, 1 minute is 60 seconds, right? So 1/10th of a minute would be 6 seconds. Dividing by 10 again, 100th of a minute would be 0.6 seconds, and then dividing by 10 again, 1,000th of a minute would be 0.06 seconds, and so the answer here is D, 0.06. A number is a multiple of 45 if and only if it's a multiple of 5 and it's a multiple of 9, okay? Because 5 times 9 is 45. Now the test for something to be a multiple of 5 is that it ends in either a 0 or a 5. All of the possible answers here end in a 5, so they're all multiples of 5. So all we really care about is which of the numbers is not a multiple of 9. Now the test for a multiple of 9 is you take the digits, so 7 in A we've got 7 plus 6 plus 5, add them together. Here I get 13, 18. Right, 18 is a multiple of 9, so that means this is a multiple of 9. So for this question, that's not the answer. We're looking for the one that's not. That digit sum test works for multiples of 3, and it works for multiples of 9. Doesn't work for other numbers, right? So you can just use that for multiples of 3 and multiples of 9. Right, okay. 6 plus 7 plus 5 is the same digit sum, so that's also a multiple of 9. 5 plus 8 plus 5, so that was also 18. 5 plus 8 plus 5 is also 18. so that's a multiple of 9. 4 plus 9 plus 5, that's also 18, so that one's a multiple of 5, so it must be E. 3 plus 0 plus 5 is 8, that's not a multiple of 9, so 305 is not a multiple of 9, and so it's not a multiple of 45. Perhaps if you were scanning across, you might have noticed that one quickly, because the digits, that one's easier to add up. So I'm going to answer this question in two ways. First is sort of one that has some geometric insight, and the other one is a bit more formulaic, and I know people sometimes are more comfortable with one way than the other here. But if you just think about starting, let's say I start here, and then I rotate around this angle, right? Now I go over in this direction, and like this line here would be parallel to this line here. So I haven't sort of made any rotation if I go around here, and then I rotate again, right? And again, sort of this line here and this line here are parallel. So sort of as I go around here, I don't rotate anymore, and then I sort of rotate again. And you can kind of see by this argument that actually by the time if I keep doing this and I add all of these together, I'm going to end up back facing in the same direction that I started, like if I imagine like looking out from these parallel lines. So these angles together do form exactly a whole circle, and so the answer here would be 360 degrees. Now, a sort of more algebraic sort of way of doing this perhaps, or using the formulae for shapes, would be that I might look at each circle here and say that like it contains two right angles, okay, and it contains this interior angle and this one that I'm looking at, right? So now if I add together all of these circles, 1, 2, 3, 4, 5, 6, 7 of them, in total I would get 7 times 360 degrees, okay? But if I look at each individual circle, right, it contains these 280 degrees, and it contains the interior angles and then this one, right? And we know that the sum of the interior angles is 180 times n minus 2, where n is the number of sides, so it's it's 180 times 5 here, right? So so you see the total of all of these angles that we're looking for, you could think of as adding together all of the circles, 7 lots of 360. I could take off 7 lots of 180 for these right angles. 7 times 360 minus 7 times 180 is just 7 times 180. Then the interior angles are 5 lots of 180, so I want to do 7 lots of 180 minus 5 lots of 180, which is 2 lots of 180, and so that's 360 degrees, and we get the same answer. So the first answer obviously is the much quicker answer. It's the one you're meant to get if you're going to really go fast through this paper, but it is possible to get there by geometric reasoning and the formulae that you know as well, so do whichever you prefer. So in this school, 315 out of the 600 pupils were girls, so I could write that fraction of girls like this, and the number of pupils in the school increases to 640, but this proportion stays the same. We want to know how many girls there are. So I could put 640 on the denominator here, and I want to know what numerator goes with that effectively to keep the proportion the same. So one way we could do this is to simplify this fraction down, 315 over 600. I could divide top and bottom by 40, or you could do by 10 and then, by 15, which gives me 40 on the bottom, or you could do it by 5 and then by 3. So if I divide top and bottom by 15 here, I get 40 on the bottom. 15 times 10 is 150, so 15 times 20 is 300. 15 times 21 is 315, so I get that's 21 over 40. Right, so actually there's two ways I could do this now, right? I could either say, well, the proportion is 21/40ths, so it must be actually that the proportion of the new students is also 21/40ths, right? So of those new 40 students, that means 21 of them must be girls, right? And so the answer here would just be 315 plus 21, and that would give me 336. Or I could multiply this fraction back up by multiplying by 16 top and bottom, and that would give me 640 on the bottom, and on the top I would have 20 times 16 is 320, plus another 16 gives me 21 times 16, And that gives me 336 as well. Actually, now I've done that question, I think this way is better, to just work out it's just to simplify the fraction and say that means that there's 21 out of the new 40 that are girls, and add them together. Right, so we want to know which of these three statements are true. Let's deal with them one at a time. So doubling a positive number always makes it larger. Well, yeah, that's true, isn't it? You know, if I take 2 times 2, I get 4. If I do a half times 2, I get a 1. You know, if I start with x, I always end up with 2x, and 2x is definitely bigger than x for a positive number, so I'm pretty convinced that 1 is true. Squaring a positive number always makes it larger. Well, you might just convince yourself that it's true by mistake here, by doing whole numbers, like 3 squared is 9, it gets bigger, 9 squared is 81, it gets bigger. But we've got to consider all positive numbers, so that includes fractions, and you should watch out for numbers that are smaller than 1 here. If you take a number that's bigger than 0 but smaller than 1, like a half, and I square it, that's a half times a half, which is a quarter, and a quarter is actually smaller than a half. So squaring makes numbers between 0 and 1 smaller, and so that one is not true. And then the same thing in 3, taking the positive square root of a positive number always makes it smaller. Again, if you just thought about whole numbers, like the positive square root of 9 here is 3, then it gets smaller. But if I could use the same example. I could use the same example here, like I now know the positive square root of a quarter is a half, and that gets bigger. So 3 is not true. Remember, it says positive square root here because if I try to solve the equation x squared equals 9, it has 2 roots. X equals plus or minus 3. So we could talk of plus and minus 3 as the 2 square roots of 9, but the symbol here, when I write it like this is correct. I shouldn't write plus or minus 3 here, because this symbol actually means the positive square root. Anyway, we can see that 2 and 3 are false, and 1 is true, so the answer is C, only I. Right, so I think it's clear here that the lines of symmetry are going to have to be here and here, and I want the shape to have these 2 lines of symmetry. Now, I'm going to do this systematically and make sure that I get all possibilities as I do this. So I'll first consider every possibility where I shade 4 squares with 2 lines of symmetry that includes this square here, right? Now, if I include this top left square, to be symmetric in this vertical line, I must include this square, right? And to be symmetric in this horizontal line, I must also include this square and this square. So actually I had no choice. If this one is included, this is the only pattern, right? So I'm going to tick off one option that I found, and now I'm going to say, well, look, I found all the options that use this square, so I'm not going to allow myself to use this square anymore. Because I'm not using this square, it actually means, of course, I can't use this one, or this one, because if any of the, well, let's say I can't use these two for sure, because if these two are filled in, then this one would have to be filled in as well, right? And in fact, you know, it means I can't use this one as well, because if this was filled in, then this one would be filled in and so with that one, right? So all of these are now ruled out. So let's consider ones where I shade this square. By the same argument, that means I'd have to shade this one, and this one. And that's the only way of doing it with that square filled in then, right? So that's the second way of doing it. And now I'm not going to allow myself to use any of these 4 squares in any future ones. And so the only option left is to shade all of these 4, and that's it then. So there are only 3 different ways. And because I've been systematic, I'm absolutely certain that there are no more. And the answer is B, 3. Right, what is the remainder when the square of 49 is divided by the square root of 49? So hopefully you just know that the square root of 49 is 7. Now 49 squared, the square of 49, is, well, it's 7 times 7 times 7 times 7 then, isn't it, right? So if I divide 49 squared by 7, it's going to divide exactly. It's just going to end up being 7 cubed. So there won't be a remainder, and the answer is that the remainder is 0. So the answer is A. Right, it says in New Threeland we've got 2p coins, 5p coins, and one other type of coin, and it's possible to make 13p out of just 3 coins, and it's also possible to make 19p out of just 3 coins. So I could think about the possibilities here, right? So if I'm going to make 13p, it can't be just 3 of the new coins because it's not divisible by 3. One of the answers, all the answers here are whole numbers. But I could have like a 2 and a 2, a 5 and a 5, or a 2 and a 5, and then 1 of the new coins. I suppose I could also possibly have a 2 and 2 of the new coins, and a 5 and 2 of the new coins. But these would be all the possibilities. So in these different cases, in this one it would have to be 9 as the new coin, this one it would be 3, this one it would be 6. Here it would have to be half of 11, so that can't work. Here, because it would be not a whole number, and here I'd have 8 left over, so it could be 4. So I can actually also obviously discount answers here that are not possible answers to the in the question here, so it's not 3. Right, I can also make 19p in the same way. So if I just change the target to 19 with each of the same possibilities, right? So 2, 2, and 15, 5, 5, and 9. Right, now actually at this point I could stop because I've found a coin that makes both of these work. So if this question has an answer, it must be D, 9p. For completeness, you might want to just check the other cases to make sure you haven't made a mistake perhaps. So here it would have to be 12. If it was 2 and 2 others, again, not a whole number, so it's not going to work. And 5 and 2 others would be 7. So 5 plus 14 gives me 19. So it's the only way of doing it. And the answer is D, 9. But as I say here, because it's a maths challenge question, if you find one way for it to work, then you don't have to carry on because you know they've designed the question, so there's only one answer. Okay, so we're going to add up all the even numbers between 1 and 101, and then subtract all of the odd numbers between 0 and 100. And so, you know, if you actually worked out those totals and subtracted them, this would be quite a hard question. Let's think about what's going on in a slightly better way then, right? So just imagine I've got all of these numbers, right, 98, 99, 100. So I'm going to look at the odd numbers and then, but they're going to be subtracted from the even numbers. Okay, so if I look at them in pairs, right, in the total, like in my total I'm going to be doing like 2 plus 4 plus 6, but then I'm going to be doing minus 1 plus 3 plus 5, right? It's going to be 2 plus 4 plus 6 all the way up to 100, but then I'm going to subtract 1 plus 3 plus 5 all the way up to 99, right? So you can think of it like I'm going to be doing 2 minus 1, and then I'm going to be doing 4 minus 3, and I'm going to be doing 6 minus 5, and adding all of those together, right? If I look at this sort of in columns instead, right? 2 minus 1 is 1, 4 minus 3 is 1, 6 minus 5 is 1. And so if I keep doing that, I'm going to be adding together all of these pairs of all of these ones. How many pairs of numbers are there between 1 and 100? Well, there are 50, so my last pair is going to be also 100 minus 99, which is 1. So I'm just going to end up with 50 lots of 1, and so the answer is B, 50. Okay, so we've got to fill in this cross number. Along the right here, we've got to have a cube number. Down here, we've got to have a square number. So it's a 3-digit cube number, a 2-digit square number, and a power of 11 that's 5 digits. So you might think the power of 11 is the hardest place to start here, but actually in some ways it's the easiest because there's only one 5-digit power of 11, right? 11 squared is 121, and then if I do 121 times 11, I get 1331. If I do 1331 times 11, I get 14641, and if I do 14641 times 11, I get something that's bigger than 5 digits. So actually I know this must be 14641. Now that is I did the calculations quickly here as well, by the way, because I know that the powers of 11 also appear here in Pascal's triangle, and I just remember what they are. So have a look up Pascal's triangle if you don't know what that is, and on my Mathsaurus YouTube channel I've actually got a video that tells you why the powers of 11 appear in Pascal's triangle like this. In Pascal's triangle you just, to get like this number here, you add together the one above to the left and above to the right. Anyway, that's not what this question's about, but you can go and look that up if you're interested. Okay, that's Pascal's triangle. Anyway, let's not get distracted from this question. So I've got a square number now that's 2 digits that ends in a 4. Well, the 2-digit square numbers, 16, 25, 36, 49, 64 and 81, so it can only be 64 now. And now I've actually got, now 1 across is a cube, so I need just a 3-digit cube that ends in 6. So, 5 cubed is 125, 6 cubed is 216, and I don't have to check any further then. Again, a maths challenge question, there can only be one answer, so it must be the case that no other 3-digit cubes work here. I mean, you can check if you want. 7 cubed is 343, 8 cubed is 512, and 9 cubed is 729, and anything bigger is more than 3 digits. So, it's one of those things, you don't, actually having memorized the square numbers up to, up to 10 or 20 squared, and the cube numbers up to 10 cubed can be useful in in maths challenges. Right, the answer to this question, anyway, 2 plus 1 plus 6 plus 1 plus 4 plus 6 plus 4 plus 1, so that's 9, 10, 21, 25, and so the answer is 25. Oh, and I just realised I didn't put the answers on the screen here actually. So here were the options. Anyway, 25 is one of the options here, and so the answer is A. So this question is not too bad if you know your interior and exterior angles stuff, but you do have to not get distracted and sort of, the answer, the question asks here for angle TVU, which is this one that looks a bit hard to work out. So I can't really go directly at that. But the things I know here, I'm drawn immediately to this point here when I look at this question. Right, we know that in a square here we're going to have right angles, and we know that we've got a 60-degree angle in an equilateral triangle. So the only other one we might want to think about a little bit is what we get inside a hexagon. So the exterior angle for in a regular hexagon here is 360 over 6, which is 60. And then angles on a straight line add up to 120, so the interior angle is 120, right? So this one's also 120. Right, so that means that this angle in here, VUT, is 360 minus 120 minus 60 minus 90, which is 90 degrees. And then you look at that and you think, right, that's why this question's not as bad as it looks, because this angle is actually a right angle, 90 degrees, and that means that this is a right-angled triangle, and actually also, and then we look at this as well and we say it's it's an equilateral triangle, a regular quadrilateral, regular hexagon. So it actually means, okay, equilateral triangle, so all these sides are the same length, but then in the square, well, all of its sides are the same length, so they must also all be the same length as this, and it's a regular hexagon, so they must all be the same length as well. Actually, okay, so it's not actually really that it's 90 degrees that makes it easy, sorry. It's the fact that it's, we can see that this triangle is actually an isosceles triangle, right, because 2 of its sides have the same length. This one has a 90-degree length, and then the other 2 must be equal. So I do 180 minus 90 to get 90, and then divide it by 2 to get what each of the other 2 are, and we see that they must each be 45 degrees, and that's the one that we were looking for. So the answer is A, 45 degrees. So in this question it says the range is 20 of these list of integers and the median is 17, and I want to know what the smallest possible number of integers in the list is. So I'm going to start with the smallest possibility here, 1, and keep working up, and I'll realise whether they're possible or impossible. So a list of 1 integer, right, so that would just be a number, right, maybe it is 17 or something, right, so the median would be 17, but it doesn't have a range of 20 because the range is the largest number minus the smallest number, so here the range would be 0. So we can't do it with 1. Can I do it with 2 numbers? Right, so with 2 numbers, how do I work out the median? Right, if my numbers were like 3 and 10, there is no middle value, so the median is the average of those, right? So it would be 3 plus 10 over 2. So here, I would need numbers that are, so we've got 17 as the median. The 2 numbers would have to be the same amount bigger than 17 and smaller than 17, right? So you could think of them as they'd have to be 17 plus x and 17 minus x, and then they'd have a median of 17. Now for the range to be 20, the difference between these two must be 20. So, I'm adding on a certain amount and subtracting a certain amount, and the total distance, right, if I think of this as a number line, I've got 17, to get to 17 plus x, to get to 17 minus x, the distance is x on each side. So for the range to be 20, I would need 2x here to be 20, so I could have 2x equals 20, so I could have x equals 10. So actually it does work here. I can do 17 minus x is 7, 17 plus x is 17, and there's my list of two numbers which have a range of 20 and a median of 17. So the answer here is B2, and we don't need to consider anything else because that's the smallest possible number of integers in the list. Right, so splitting things up into triangles is a top maths challenge trick for sure when you've got reasonably nice shapes, and that's what I'm going to do here. We're told that the angles in the trapezium are 60 and 120, so you can see I can actually split this trapezium really nicely into three equilateral triangles for that reason, right? This angle here is 60 and this one is 120, which is two lots of 60. If I think about it that way, and then I think about this bigger shape, I can also split all of these into equilateral triangles. I mean, I'm only really interested in the ones that are on the perimeter, but perhaps I'll fill them all in. Why not? You could, if you are doing this quickly in the challenge, you can just think about the ones that are on the perimeter, because that's all that matters here. So if I look at the perimeter of the big trapezium now, right, each of these individual sides of a equilateral triangle I could call x here, and just count how many of those I've got as I go around. Right, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the perimeter of the big trapezium here is 15x, whereas for the smaller one it's 1, 2, 3, 4, 5x. So the perimeter of the small trapezium is a third of the perimeter of the large trapezium. We know that was 18, so I just have to do 18 divided by 3, and that gives me 6 centimeters, because so 6 is a third of 18, 5x is a third of 15x, right? So anyway, I hope that makes sense. If you just count the small sides of the small triangles that make up each of the perimeters here, we get that argument, and the answer is C, 6 centimeters. Right, so we have some unicycles, bicycles, and tricycles. Now, each of these will have one saddle each. So if I let the number of unicycles be U, bicycles B, and tricycles be T, then when I add those together I must get 7, because there are 7 saddles. Each one of these has a saddle. 13 wheels in total. Unicycle has 1 wheel, bicycle has 2 wheels, and a tricycle has 3 wheels. So if I do number of unicycles plus 2 times the number of bicycles plus 3 times the number of tricycles, that gives me the number of wheels, and that must be 13. And we also need the number of bicycles to be bigger than the number of tricycles. So I'm going to do this by just trial and error now, because there's not going to be that many possibilities. Right? U plus 2b plus 3t is 13. Right, for t, okay, t is going to be smaller than b, so I'm going to start with smallest values of t, but there are only 4 multiples of 3 lower than 13 anyway, so I bet I'm going to find the answer pretty quickly by doing this. So let's just try t equals 1 and then b equals 2, so that would give me 2 plus 3, that would give me 4 plus 3 is 7, and then u is 6, but that doesn't add together to give 7. 6 plus 2 plus 1 is not 7, right? So okay, I need b to be bigger than t, but perhaps it could have been 3, and that would be 3 plus 6 is 9, and then plus another 4 gives me 13. Oh, and look, I've actually, oh no, not quite. 4 plus 3 plus 1 is 7. So that doesn't work. Maybe I could have 4 here. 8 plus 3 is 11, plus 2 gives me 13. So 2, 4, 1 works. And actually 2 plus 4 plus 1 is 7. So there we go. I've got the answer here. There would be how many unicycles? So the answer is B2. Now you might say, well, hang on, aren't there any other possibilities? If I was giving a really good mathematical answer to this problem, yes, I'd have to go through and I'd want to check that I can't make this work in any other way either. Maybe I'd start trying 2 tricycles, and 3 tricycles, and just keep going until I've exhausted all possibilities. But it's a math challenge question. There can only be one answer, so this must be it, and I can stop there. And actually, you might say I was lucky here. I got the answer so quickly, but I did follow some good instincts and do it in a very sensible order, right? Looking through multiples of 3 because there are fewer multiples of 3 than anything else, starting with small values of t because I know the numbers that the value of b has to be bigger than t, right? So my search was efficient and it was guided by the problem, and that's our aim if we're going to do these super efficiently and leave ourselves some time to have a go at the hardest problems. I mean, this is one of the hardest problems, but still we're trying to do it in the best way possible. So which numbers get more than one mark here? Well, it's got to be something that's both a multiple of, either a multiple of 3 and a multiple of 5, or a multiple of 5 and a multiple of 7, or a multiple of 3 and a multiple of 7, or possibly a multiple of all of them. Right, so if something that's a multiple of 3 and a multiple of 5 is a multiple of 15. Okay, so multiples of 15 get 2 marks. Multiples of 3 times 7, which is 21, get 2 marks, and multiples of 35, which is 5 times 7, get 2 marks as well. So we can just write these down quickly, I think, here. 15, 30, 45, 60, 75, 90, 105, 120, 135, and 150 all get 2 marks there. 21, 42, 63, 84, 105, 126, and 147 will all have 2 marks, and 35, 70, 105, and 140 will also all have 2 marks. And I've just got to be careful that I don't overcount these, because 3 times 5 times 7 is 105, and that's going to be in all 3 of these lists here, right? So I don't want to count it twice, so 3 times, I just want to count it once. So I'm just going to count these up then. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and the answer is E, 19. So this is probably the hardest question in this paper to actually explain, because you have to sort of visualize what happens when you cut through a cube, right? So, the idea here is that I've got something sort of roughly cubical here, and, can I, so this one doesn't have a base, but, can I cut through the cube and get this shape? And you can sort of see that, if I just cut a wedge off the corner here, you can imagine sort of getting a triangle, when I take that plane cut through. So you have to just think about, are there other ways of cutting through that give you each of these shapes? I guess I can get a narrower triangle by doing something similar. And actually all of these are possible, and if you visualize them, they look something like this. So you can cut off that corner. If you cut the corner off and go right up to the top there, you can get the trapezium, and you can get this hexagon by making a cut like that. So kind of a hard question. You've got to do your best to visualize it. Try practicing this before the real test by just sort of looking at a cube and thinking about different ways of slicing it through, and just do your best with that one. But you can see from all the pictures here that all 4 are possible, and so the answer is E. So a very hard question to finish with, as always here. So let's think what's happening here. I'm going to draw a little picture. We've got Exeter on the left here. So Sam starts there, and he travels at 25 miles per hour, perhaps she, I suppose. And London, we've got Morgan, who's going to be travelling 35 miles an hour in the other direction, and there's 175 miles between them. Right, so the first simplification I'm going to make in this question, okay, we've got Sam leaving at 10 a.m. and we've got Morgan leaving at 1 p.m. at 1300. Right, so actually by 1 p.m, right, Exeter, so Sam will have gone 3 hours from Exeter. So in 3 hours he'll have done 3 times 25 miles per hour, which is 75 miles. Right, so actually let's just say, rather than being in Exeter at 10 a.m, let's say Sam is somewhere else, and the distance is only now 100 miles between them, right? So at 1 p.m, Sam is going to be somewhere else, still traveling at 25 miles per hour, but the distance between them is only going to be 100 miles an hour. Right, now there's a really key idea that comes up in these sorts of problems. This is almost a classic sort of maths problem that people find difficult and dislike, but when you realise the trick, it's kind of nice. So if 2 objects are traveling towards each other at certain speeds, and I want to know when they meet, right, all I have to do is think, well, okay, at this point where they meet, wherever it is, together they will have travelled 100 miles. Right, Sam is covering 25 miles every hour, and Morgan is travelling 35 miles in every hour. So between them, they are travelling 25 plus 35, which is 60, miles every hour. And as soon as they've covered that whole 100 miles between them, they will meet. Right, so we actually just need to know how long would it take to travel 100 miles at 60 miles an hour. Okay, so we can do 100 divided by 60 here, right? So speed equals distance over time, or I suppose I'm using here time equals distance over speed, a rearrangement of that. 100 over 60 is 10 over 6, which is 5 over 3, so that's 1 2/3 hours. 1 2/3 hours is 1 hour and 40 minutes. So at that point they will be together, and 1 hour and 40 minutes after 1 p.m. is 2:40.